Hi folks, it's Mr. Ray here. We're going to continue on in data management. We are working in Unit 2, which is Introduction to Probability. The previous lesson we did, looking at the probability of events, was a very important lesson. A lot of what we do in the next two lessons and beyond uses that formula, which we conveniently have here as our first definition. So the probability of event A is the number of times A happens over the total possible outcomes. So that will be a fraction, decimal, or percent. Either of those three is okay. What we're going to do in lesson 4 and continue with lesson 5 to finish the unit, we'll be looking at two events at the same time. So this lesson will be looking at whether the two events are independent or dependent to each other. So anytime we involve more than one event, we call it a compound event, compound meaning more than one. We'll only be, well, we're mainly focusing on two events. Okay, so we're going to be looking today at how do we calculate the probability of the two events happening at the same time. Okay, well, not at the same time, but both of them happening. Okay, so those two events can either be independent or dependent. So I'll start with dependent. So dependent means, actually no, I'll start with independent. Independent means that the two events have nothing, they're not, the probability of either one happening doesn't depend on the other event happening or not happening. For example, you could have probability of choosing a heart from a deck of cards and the looking at the probability of flipping it ahead when you flip a coin. So obviously those two things have nothing to do with each other. So whatever the probability of each of these separate events is, we can end up just multiplying those probabilities together to see what's the probability of both of them happening. Okay, so this is independent. Now, if you have dependent events, that says they have an impact on each other's probability of occurring. So a good example of that would be maybe the first event is choosing a 7 from a deck of cards, and the second event is choosing a second 7 from that deck of cards. So you can see that choosing the second 7, that probability will depend on, did you pick a 7 in the first event? Because if you did, you'll have one less 7 that you can choose. And if you didn't pick a 7 in the first event, well, then you'll still have 4 to choose from. So that probability for B is changing depending on what happened with the first event. So we call those dependent events because they depend on each other. And there's a slight variation on the formula. So the probability of A and B happening is the probability of A happening. And then we've got this funny looking thing. This basically says it's the probability of B occurring given that A did occur. So you can see that dependency there. So we'll work with some examples that use that. So the important thing when you're getting a question where you're finding what's the probability of two events happening, both of them happening, well, the first thing you'll have to do is figure out, are these independent or dependent events? Because based on what your answer is, you will be using a different formula for that. So this lesson is all about, as you can see here, probability of A and B. Okay, so obviously two events, compound events. Tomorrow, or the next lesson we do, when we look at whether two events are mutually exclusive or not, that will be calculating the probability of A or B. Okay, so they don't have to both happen, but what's the probability of either one of them happening? So that will be in lesson 5. This lesson is really dedicated to the probability of A and B and the two formulas associated with that. Okay, so these two things I've already talked about. Now you can, if you wanted to, well, you could actually rearrange any of these formulas, but This one here is a little more interesting. So if I took the dependent probability of A and B, I could isolate for probability of B given that A happened. I could isolate that as the left side, and I could see that in order to get that, I have to use take the probability of A and B happening and divide it by the probability of A. So sometimes you might be asked to actually calculate that based on knowing these two already. Okay, so let's look at some examples. So we've got quite a few examples today, just to make sure everybody has a good understanding of this. So, this event, these examples, and also the examples on the next lesson, I kind of spilled the beans here. I tell you up front in the example whether it's independent or dependent. Now, you won't be so lucky when you get a question on a test or a quiz. You'll have to figure that out for yourself. So we will kind of assume that we don't know this, even though it's listed in the example. I put it in the example just so when you're using these as study notes, you can go and find, oh, let's look at some examples of simple independent events. Okay, so the simple part here, that's different from compound. Compound means more than one event. This is just one event. Now you could be doing this over and over, but it's just the same event, just one event. Okay, so part A, a coin is flipped and turns up heads. What's the probability that the second flip coin will turn up heads? Okay, so we already know that the first coin was flipped and turned up heads, so that's a given. So the fact that you're calculating the probability of the second coin also turning up heads, you might think, well, maybe there's a less chance that it turns up a head because the first one already was. Well, that would be false, because flipping a coin, we call this a memoryless event, which means what happened previously doesn't matter. So I could flip 25 heads in a row, and if I flipped a 26th time, it still would have a probability of 1 out of 2, because there's two outcomes. There's one of them which is a head. So what's the probability the second coin will be a head? Well, that's 1/2. Okay, which you could write as 0.5. Okay, and we continue this. The coin is flipped 4 times and turns up heads each time. Well, we sort of talked about this already. What's the probability that the fifth try will be heads? Well, it's the same as the probability of the second, third, and fourth times, and the 100th time, it's always going to be 1/2 or 0.5. Okay, because it doesn't care what happened in the past, because it doesn't influence the probability of in this case, the fifth flip. All right, find the probability of tossing 5 heads in a row. This is a slightly different question. So in this case, we have to look at all 5 of the flips. Okay, so the first toss or flip, probability of getting that as a head would be 1/2, just like any other time. Okay, and then what we do is we multiply by the probability of the second flip being a head. That's also 1/2 times the probability of the third head. Right, so this just continues however number of flips we do. So it's 5. I could have just written this as 1/2 to the power of 5, because I'm multiplying the same thing by itself 5 times, and this is equal to 1/32, which, if you want to do a decimal, that would be 0.03125. Okay, so obviously that's a lot less than 1/2, because you're actually looking at, it would be pretty rare to flip, well, you're looking at 5 flips instead of 1 being a head, so that's the big difference. You notice it's the number of flips is the exponent here. I could have put to the power 1 because it was 1 flip for each of these. Now, comment on the differences between the answers in B and C. Well, I think we've talked about that. Even though we flip 5 coins here, the probability that we're calculating here is just the probability that the fifth head is the fifth flip is a head. We already know that what happened in the first four, but that's not part of the probability. Whereas this, you're looking at all 5 tosses being heads. Okay, so if I put that in words, the B calculates the probability of just the fifth toss being a head. Okay, whereas C calculates probability, so they're both probability calculations. Of 5 tosses being heads. Okay, so hopefully that's clear. Okay, example 2, and this time we're looking at compound, which means more than one event, and we're kind of being spoiled by being told they're independent. The previous one was, example 1 was independent too, but in this, each of these flips is considered a separate event. So this time we've got 2 different types of events. So it says a coin is flipped while a die is rolled. What's the probability of flipping heads and rolling a 5 in a single trial? So this is sort of the example I gave when I was defining what independent events are. The probabilities of each of them have nothing to do with the other probability, whether or not it happened or not. Okay, so I'm actually, when I have compound events, I'm going to write out what the event is. So the first event was a coin flip is a head. And the second event, B, is rolling a 5 with a die. Okay, so I want to, well, first I do what I just talked about, determine, do these 2 things, does whether or not this happened affect the probability of this happening or vice versa, or are they independent? And they are independent because flipping a head will not influence whether or not you rolled a 5 or not, and vice versa. So since we've come to that conclusion, since A and B are independent, that means that when we do our, so before I write this out, it says, the question is, what's the probability of flipping heads and rolling a 5? So we could basically replace flipping heads with event A and rolling a 5 with event B. So this is basically saying, what's the probability of A and B? Okay, so that's what I'm trying to calculate here, so that they both happen. So from the formula that we had in the first page for independent events, we know that we just multiply the 2 separate probabilities of A and B. So what are those? So the probability of flipping a head, well, we've talked about this in the previous example, that's 1/2. And probability of rolling a 5, well, a die has 6 outcomes. A 5 is one of those 6, so 1/6. So I multiply those out, I get 1/12, which I could round as a decimal to 0.083. And if I put a conclusion here, therefore there's an 8.3% chance of flipping a head and rolling a 5. Okay, so to summarize, the 2 events that are being talked about in this question are independent because they do not influence each other's probability if they do or do not happen. So since they're independent, we can use the formula for independent events, which is probability of A and B is equal to probability of A times probability of B, And we get that there's an 8.3% chance of both of these happening. Okay, on to example 3. Okay, so again, spoiled. We know this is going to be independent, but let's talk about it so you know how to determine that yourself. Su Ling travels the same route to work each day. She's determined there's a 0.7 probability that she will wait for at least one red light, and there's a 0.4 probability that she will hear her favorite new song on her way to work. First part is, what is the probability that Su Ling will not have to wait at a red light and will hear her favorite song? Okay, so I'm going to define the events here. And instead of define them around the way the question's worded, I'm going to just define them the way the information was originally given. So the first thing was a 0.7 probability she will wait for at least one red light. So event A, I'll define that as she will wait for a red light. Okay, and event B, there's a 0.4 probability that she will hear her favorite new song on her way to work. So I'll make event B is she hears her favorite song. Okay, now over here, I'm going to write down the probabilities. So the probability of A happening, that she waits for a red light, they told us that's 0.7. And the probability of B happening, she hears her favorite song on her way, is 0.4. Now, let's address the question now. What's the probability that Su Ling will not have to wait for a red light and will hear her favorite song? So we have to be careful here, because what they're asking here is not event A, it's the opposite. So instead of she will wait for a red light, it's she will not have to wait at a red light. So what we're actually using there is A prime, or A complement. That's the everything else. So I'm going to put down what the probability of not waiting at a red light is going to be 1 minus probability of waiting for a red light. So that's 0.3. So 1 minus that. And just in case I have to use the complement of B, I'll put that here now. That's 1 minus 0.4, or 0.6. Okay, so back to the question. What's the probability that Su Ling will not have to wait at a red light? So that's A prime. And we'll hear her favorite song. That event is B. So I'm looking for probability of A prime, or A complement, and B. So I had to kind of work with, make sure we got the right event here, so we use the right probability. So now we've already talked about, or sort of talked about, are these independent or dependent? Is waiting at a red light, will that have any impact on the probability of hearing her favorite song? Well, it doesn't appear so. So we know they're independent. So we're going to use our more simple formula of just multiplying the two probabilities together. And I'll just put in brackets independent. Okay, so probability of A prime, we've already put that there, 0.3. And probability of B is 0.4. And that's equal to 0.12. So therefore, there's a 12% chance of not waiting at a red light. And hearing her favorite song. Okay, so this is a good question because it gave the probability of something happening, but it was asking about the complement happening. So that's why it's so important to put, at least assume or pick one of those sides to be event. Actually, you've got 2 events. And then if you need to use the complement, you can calculate the probability based on the probability that was given to you. Okay, so second part, what are the odds in favor of Suling having to wait at a red light and not hear her favorite song? So this is an odds question. So anytime you have a question that they give you the probability and ask you for the odds, but you have to do some work, well, we're going to work with the probabilities. We're going to convert the odds to probability. Sorry, that's not right. We're going to do our calculation with the probabilities, and then when we get our final answer for the probability, we convert that to odds. So in this case, if I'm talking about the probability of this, it's Suling has to wait at a red light. So that is event A. So probability of A. And not hearing her favorite song. So remember, B was she hears her favorite song. So in this case, it's the B complement. So probability of A and B complement happening. And this is still, these events are still independent. So we just multiply the 2 probabilities. This time we use probability of A times the probability of B. Get that right. Times the probability B complement. So we go back here, and it's really good to document this so you don't have to do the calculation more than once. The probability of A is 0.7. Probability of B prime is 0.6. Multiply that out, we get 0.42. Now, I'm not quite done because I can't just say there's a 42% chance of this happening, or 0.42, because they wanted an odds. So when you asked for the question of odds, it's really beneficial to have your probability in as a fraction. So I have it as a decimal right now because the original probabilities were decimals. So I'm going to write this as a fraction, which so I'm going to write this as a fraction. And when it's given as a decimal, that's easy to do because you can write the decimal over 10 or 100 or 1,000, depending on how many decimal places you have here. So this would be 42 over 100. I can reduce this to 21 over 50, which you should do to make your numbers easier to work with. Okay, so what does this probability of 21 over 50 mean? It means the probability of this happening will be successful 21 times out of 50. So it'll be successful 21 times and unsuccessful 29 times. So the top number is success, and so the failure will be 50 minus 21 equals 29. Those will be the times it doesn't happen. And that's what we need for the odds. We don't really do anything with the 50. We work with the 21 and 29 as our ratio. So the odds in favor, because that's what the question said, odds in favor of waiting, I gotta just shorten this so it fits, of waiting, which stands for waiting for red light, and hearing favorite song are, so in favor means you put the ones where you succeed. So we put the 21 as our first number to the left of the colon, and our second number will be the failures. For every 21 successes, there's 29 failures. So that's what we put for the odds. Okay, there you go. Okay, these odds questions will pop up from time to time, but it's really just a matter of taking your probability and turning it into odds, or taking your odds and turning it to a probability, working with those, and then changing it back to odds. So, all right, example 4. We have a professional hockey team has 8 wingers. 3 of these wingers are 30 goal scorers, or we'll call them snipers. Every fall, the team plays an exhibition match with the club's farm team. In order to make the match more interesting for the fans, the coaches agree to select 2 of the wingers at random from the pro team to play with the farm team. What is the probability that the 2 snipers will play for the farm team? Okay, so there's one thing happening here, but there's 2 parts to that. You might think the event would be selecting 2 wingers, but we're going to divide that up into 2 separate events. So I'm going to say A is the event where the first winger is a sniper, and B will be, very similarly, that the second winger is a sniper. Okay, and the reason why we do that is because you can see that when I select my first winger, if you look at the numbers here, so there's, how many wingers are there? There's 8 wingers. So when I select my first winger, the probability that that winger is a sniper is 1 out of 8. Okay, so this will always be a probability of 1 over 8, but this probability of selecting the second winger is a sniper, well, that depends on what happened here, because if we didn't select a sniper here, well, there's still 3. Sorry, I think I said 1 out of 8. There's 3. So the probability of event A will be 3 out of 8. Now, if I don't end up selecting a winger with the first selection, sorry, if I don't end up selecting a sniper with my first selection, I've still got 3 snipers that I could pick from for the second pick. So the probability of selecting a sniper for the second winger would also be 3/8. Okay, so in that case, the probabilities are the same, 3/8 and 3/8. But if we actually did get a sniper when we chose our first winger, then there's 1 less sniper to choose from. We're down to 2. So that means the probability of selecting the second winger as a sniper will be 2 out of 7 instead of 3 out of 7. Okay, so let me get this straight. So probability of selecting the first winger being a sniper will always be 3 out of 8. This probability, I think I might have messed up on the denominator. You've got 1 less winger to choose from, so you're down to 7 to select from. So it's either going to be 3 7s or 2 7s. It'll be 3 7s if you didn't pick a sniper here, but it'll be 2 7s probability if you did, because you've also got 1 less sniper. So because of the dependency, that means these are dependent events, okay? Which we already knew from the title, but so you're going to have to figure that out when you get a question on a test, or a homework question. So the probability, what's the probability that 2 snipers will play for the farm team? Well, that's just combining the 2 probabilities. So probably the first winger is a sniper and the second winger is a sniper is really the same as probability of A and B. Okay, guess I should put a B there. Now, because these are dependent, I can't use just probability of A times probability of B. That's not going to work this time. So the formula is slightly modified. If you remember from the first page, it's probability of A times the probability of B given A happened. Okay, so remember I said we had 2 different probabilities for B, so we're going to use the one where we actually did pick a sniper. So if you remember, the probability of A was always going to be 3/8 because there's 3 snipers out of the 8 wingers, and since we know that A happened based on this statement here, probability of B given that A happened, so we're basically know that we've already selected a sniper here, so that means we have 2 snipers left out of the 7 wingers to choose from. Okay, so that's equal to 6 over 56. Can reduce that to 3 out of 28. And then do our calculator. So we get approximately 0.107. So to conclude, there is a 10.7% chance that 2 snipers will play for the farm team. Okay, so that's the first question we had where we actually had to use this formula because it was 2 dependent events. The previous ones of our compound, 2 compound events had been independent, so we just multiply the 2. So you can see this is a little bit trickier. Not a whole lot, but you have to use a different formula. Okay, let's go to the last page. So we've got 2 more examples to go through. Okay, example 5. So you can see I'm not really claiming the answer, and you'll see why when we do this. A bag of colored marbles has 5 red marbles and 7 blue marbles. What is the probability of selecting 2 blue marbles in a row if the first blue marble selected is not put back in the bag before the second marble is selected? So basically, you're trying to calculate the probability. You stick your hand into this bag of 5 red and 7 blue marbles. You pull out a blue marble. You take that blue marble out, set it on the table. Then try again with the remaining marbles and pick a second blue marble. So what's the probability that happens? Okay. Is this compound event independent or dependent? So we'll define our events here, which we'll actually use for both questions. So the event A is the first marble is blue. And very similarly, event B is the second marble is blue. Okay, so when you're thinking about is this independent or dependent? So if it's not put back, well, what's the probability the first marble is blue? Well, there's 7 blue marbles out of 12, so that probability would be 7/12. Now, if I choose one of those 7 and I don't put it back in the bag, well, the probability here changes, right, to become 6 out of 11. So, but if I don't choose a blue marble here, then it's 7 out of 11. So you can see that the whatever happened here affects the probability of the second event. So therefore, this event is independent. Oh, sorry, I had the wrong way. This event is dependent. They depend on each other. Okay, maybe make that darker. So this is dependent. So that means when we calculate the probability of A and B, then we use the formula for dependent events, which is the one we just used on our last question. So probability of A, so first marble, we have 12 marbles to pick, 7 of them are blue, so the probability is 7 out of 12. When we go to pick our second marble, the fact that this is given that A happened means the first marble was blue. So now we've got 6 blue marbles left to choose from, and since we took that marble out, we're down to 11 total marbles in the bag. So that's equal to 42 over 132, which is 0.318. Okay, so for this, if you don't put back the blue marble that you just picked, the probability is 31.8% chance. Both marbles are blue. Okay, now second variation, very similar. What's the probability of selecting 2 blue marbles in a row if the first blue marble selected is put back in the bag before the second marble is selected? So what happens here, we stick our hand in, pull out a blue marble randomly, and then just make a note that we picked a blue marble, put that blue marble back in, and then put our hand back in and pull out another blue marble. So in this case, since we put back the blue marble, in both cases, we have, before we pull a marble out, we have 12 total marbles, and in both cases, we have 7 blue to choose from. So it's the same probability. So in this case, it doesn't matter what happened with the other marble. Whatever happened does not affect the second probability. So in this case, we are independent because we put back. So one of the ways we define this, there's lots of these types of questions. We would say this is with replacement. And conversely, this one would be without replacement, because once we choose a marble, we do not put it back, we leave it out. So without replacement is always going to be dependent, and with replacement is independent. They're closely related. Okay, so in this case, since they're independent, I just multiply the two probabilities. So probability, so I'm going to use the same definitions for A and B. So probability of A and B happening, in this case, is probability of A times the probability of B. Now, we've already talked about the numbers here. So just like the first time, previous example here, the first pull we have a 7 in 12 chance of getting a blue marble, as before. But this time we put that blue marble back, so now we have 7 blue marbles, 12 total marbles. So we still have the same probability to select the second marble being blue. So that's 49 over 144, which is equal to 0.340. So therefore, a 34.0% chance that both marbles are blue. And hopefully that makes logical sense, because if you put back the blue marble, you should have a higher chance of selecting a second blue marble, because you have seven blue marbles in the bag compared to 11 in the other case. So you would expect that should be higher just because there's more blue marbles to choose from. Okay, last example here. This one's a little bit complicated, but let's go through it together. Serena's computer sometimes crashes when she was using her email program. When the email program hangs, Serena is usually able to close it without a computer crash. She learns from her friend that the probability of her email program hanging in any 15-minute period is 2.5%, while the chance of her email program hanging and the computer crashing in any 15-minute period is 1%. Question is, if her email program is hanging, what's the probability that the computer will crash? Okay, so a lot of stuff there. We're going to start off with, there's two things happening here. There's the event of her email hanging, and there's also her second event, her computer crashing. So I'm going to define those first. So the email program hangs is the first event. And B is the operating system fails. Okay, and they've told us, if we read, she learns from a friend the probability of her email program hanging in any 15-minute period is 2.5%. So that's event A. So the probability of event A is 2.5%. Or if I change to a decimal, it would be 0.025. And then further on, it says, well, the chance of her email program hanging and the computer crashing in any 50-minute period is 1%. Well, that's not what this is. So probability of B, we don't actually know that yet. It wasn't given to us. But what they told us here, what this 1% is that if her email program hangs, let me get this right. Well, the chance of her email program hanging and the computer crashing in any 50-minute period is 1%. Okay, so we know it's kind of the email program crashing could impact the computer crashing, right? So what they're actually giving us here is the probability of her operating system failing given that her email program hangs. So what that is, if we change it back to A and B, probability of B happening given that A happened. So that's what they actually told us. And they said that that probability is 1%. Okay, so we know these are interdependent on each other because of that information, that one will cause the other one. So I'm going to write out, so this is going to be, well, we knew from up here, but it's dependent, which we could tell from the write-up. So the probability of A and B, I'm just writing out the same formula we always write out. This one is for the dependent. So it's probability of A times probability of B given A. Okay, now let's fill in what we know. So we actually, this time we do know this. Oh, I'm sorry, I messed this up. I wrote down the wrong thing. Okay, so what they told us, if I read this again correctly, well, the chance of her email program hanging and the computer crashing. So email program hanging, that's event A. Computer crashing, well, that's the same as that, is B. So what that information was probability of A and B. Okay, they're both happening. So that probability was 0.01, 1%. So I've got probability of A and probability of A and B happening. So I'm going to fill those in here. 0.01 is equal to 0.025. Now, they didn't give us this, even though I thought they did originally. So I'm just going to write that out as it is. So what I'm going to do is rearrange this to have our unknown as isolated on one side. So probability of B given A is, I'm going to divide both sides by 0.025. So that's what this looks like. Now, if I actually calculate that, that works out to 0.4. Now, hopefully that's what they asked us, because I didn't really work with what they're asking us and calculate that. I basically just started with a formula, filled in the two of the three things I knew, and then isolated for the third thing. And now we just kind of cross our fingers and go back. And hopefully that is what they asked us, because that's all we can really get from this question. Okay, so if I read the last question, if her email program is hanging, so that's a given, what is the probability that the computer will crash? So what they're asking us is, this is the probability of computer crashing, which is B, given email program hangs, which is A. So this is actually what they're asking us. This is what they're asking here. So if I tie that back there, that's exactly. So I mean, we couldn't have answered anything else given that this formula only had one unknown to solve for. So luckily that's what we got. It's actually would be a lot harder to try to start with what they're asking, I think, and work your way backwards from what we did. I think just writing down what we do know and then write out the formula for probability for dependent events, fill in what we know, and solve for what we don't know, and then see that, yes, that's what they asked us. Okay, so there's a 40% chance that the operating system will crash if her email program hangs. Okay, so this was a tricky one. It was tricky in understanding what's going on, but it was also tricky in working out the answer, because this was the only question we had where we were given probability of the two events happening, and we had to solve for something else, which was probability of B given A. So this was a tricky one, but I know there's at least one homework question where you have to do some rearranging to solve for the unknown. Okay, so look at some practice questions here. And just to summarize what this lesson was all about. So we're looking at compound events, two events. Usually we call them A and B, but we don't have to. So what we're able to, if you look at both of the formulas we were learning all the time and what we actually calculated, we can use this lesson to actually predict the probability of both of those two events happening together, probability of A and B in both cases. Now we had to use a different formula to get that, depending on whether the two events were independent or dependent. Just remember, dependent means that one of the probabilities is affected by the other, whether or not the other event actually was successful or not. So if you see that when you're looking at the probabilities that one of them changes depending on what happened previously, then you know they're independent. But if the two probabilities are always going to be the same, no matter what happened with the other event, then you know they're independent, and you can use the simpler version. Okay, so that's it for today. The next lesson will be lesson 5, where we look at mutually exclusive or not mutually exclusive, and that lesson will be used for a similar probability of two events, except it's not probability of A and B happening, it's probability of A or B happening. So once you're done that lesson, you'll have, in your toolbox, you'll have formulas for probability of both events happening or either one of them happening. Okay, so have yourselves a good day. We'll see you next lesson.